Welcome to the Health Headliner podcast by Tudu Digital. Our content is informational only and not medical advice. Please consult your provider. Now, let's dive into today's headlines.
Welcome to the deep dive. Today, we're looking into something really quite remarkable, a potential game changer in organ transplantation.
We are. It's focused on enzyme technology, specifically how it might help create universal donor kidneys.
Which could, fundamentally change the whole issue around blood type matching.
Exactly. It's a fascinating piece of science with huge implications, especially for those long waiting lists. You really need to understand the situation patients face now to grasp the importance.
It's a tough reality, isn't it? It really boils down to two things. First, getting an organ is always a race against the clock. Sometimes it's just hours.
Absolutely critical hour. And second, for so many people, that race is massively complicated by something they can't control at all, their blood type.
Yeah, and the numbers are pretty stark. The sources we looked at highlight that over half, more than 50% of patients waiting for a kidney are type O.
And that's the crux of it. Because if you're type O, you can only receive a kidney from a type O donor, period. Your immune system rejects A or B types.
Which leads to these terrible waiting times. We're talking, 2 to 4 years longer on average compared to other blood types.
That's right. And the tragic reality is that many people, many type O patients, just don't make it. They die waiting for that compatible organ. It's a real inequity baked into our biology.
So the central problem is that mismatch, that scarcity of type O organs. But the solution we're diving into today flips the script. It uses engineering.
Instead of just hoping a rare type O organ turns up, the researchers essentially asked, well, what if we could take a more common type A kidney, for example, and chemically clean it?
Clean it, like remove the thing that causes the incompatibility.
Precisely. Convert it into a universal type O organ before it even gets near the patient.
Okay, that's the big idea. And today, we're digging into the first results from a human test of this exact technology. We're pulling from recent news reports, but also, importantly, the detailed scientific paper in Nature Biomedical Engineering.
Yes, that paper documents the work from researchers at the University of British Columbia. The announcement came in October 2025, detailing how they use these special enzymes on a deceased donor kidney.
So this isn't just theory anymore. They've actually tested it in a human context, which is a massive step towards potentially expanding that donor pool. All right. Let's get into the why behind all this. Section 1. Why does blood type compatibility matter so much for a whole organ? We hear about it for blood transfusion, sure, but what makes it so, catastrophic for a kidney?
Right. It's like the body's internal ID system, but the consequences are way higher with a solid organ. Think about the blood vessels inside the donated kidney. Their surfaces, the endothelium, are coated with these specific sugar molecules, antigens.
And those antigens are the blood type name tags. So type A has A-antigens, type B has B-antigens.
Exactly. And if you're type O, you don't have A or B antigens on your own cells. But crucially, your immune system has powerful preformed antibodies floating around against both A and B. They're always there, like sentinels.
So if a type O person gets a type A kidney, those sentinels see the A name tag immediately.
Instantly. And they attack. It triggers what's called hyperacute rejection. It is the absolute worst case scenario in transplantation.
How fast is hyperacute?
Minutes.
Yeah.
Sometimes it happens right there on the operating table. The antibodies bind, they activate this other part of the immune system called complement, and it just shreds the lining of the blood vessels in the new organ.
Leading to
massive clotting, blood flow stops, the organ tissue dies, it literally turns black. The transplant fails right then and there. Irreversible.
Wow. Okay, so there's no fixing that.
Wow.
And because type O patients have antibodies against both A and B,
they're completely blocked from receiving organs from type A, type B, or type AB donors. They're absolutely restricted to type O organs only.
Which are themselves universal donor organs, meaning that they get used for everyone else too, making them even harder to get for the type O patients who desperately need them.
It's a terrible bottleneck. And that's what led to the older strategies, the ones focused on trying to, modify the patient to accept the incompatible organ.
Right, that's the ABO incompatible or ABOI approach, the recipient-centric one. How does that work, and why isn't it solving the problem for most people on the waiting list?
Well, it's incredibly demanding. To do a traditional ABOI transplant, you have to prepare the recipient for days beforehand. It involves things like plasmapheresis.
That's where they filter the blood.
Exactly, to physically pull out those anti-A or anti-B antibodies. And alongside that, you give very, very strong immunosuppressant drugs even before the transplant.
So you're basically knocking down the patient's entire immune system, hoping it won't attack the new organ.
Pretty much. And that's incredibly risky. You dramatically increase the danger of serious infections, bleeding complications. It's a heavy burden on the patient.
It takes days, you said.
Yes, several days of preparation, which immediately rules it out for most deceased donor organs. Those organs are only viable for a matter of hours, maybe a day with machine perfusion. You just don't have the time for that intense recipient prep.
So traditional ABOI is mostly limited to living donor situations where you can schedule everything perfectly.
That's generally been the case, yes, which doesn't help the majority waiting for a deceased donor kidney.
Which brings us back to the UBC approach. It's not just a tweak, it's a whole different philosophy. Donor-centric, not recipient-centric.
That's the paradigm shift. Change the organ outside the body. Remove the offending name tag before the transplant. If you do that, you potentially skip the need for that extreme patient prep.
Meaning the transplant could happen much faster, more like a standard compatible transplant.
That's the goal. And crucially, it opens the door to using those readily available but previously incompatible organs from deceased donors.
Which directly tackles that fairness issue, that biological lottery that's kept typo patients waiting so much longer.
Okay, let's dive into the core science here, the molecular toolkit that makes this possible. We need to understand these enzymes and the journey to finding them.
Right, this wasn't an overnight discovery. It builds on over a decade of work, largely led by Dr. Stephen Withers, who's a chemist, and Dr. Jayachandran Kizakadathu, a pathologist, both at UBC.
And their initial focus wasn't even organs, was it? It was blood.
Correct. They were first trying to find ways to convert donated typo blood into universal typo blood for transfusions, a huge challenge in itself.
But the breakthrough for organs came in 2019. They found specific enzymes that were unusually effective. What were they and where did they come from?
They identified 2 key enzymes, and rather remarkably, they found them in bacteria that live in the human gut. So these are naturally occurring biological tools.
Gut bacteria. Okay, what are these enzymes called?
The names are a bit technical. One is FP-galactosidase, and the other is FP-galactosaminidase. Right, let's maybe stick with the analogy. You said the A-antigen is the name tag. How do these 2 enzymes working together get rid of it?
Okay, think of it like a 2-step process. The A name tag is chemically defined by a specific sugar called N-acetylgalactosamine. That's the bit that makes it A.
Got it.
The first enzyme, the deacetylase, does a little preliminary chemical tweak. It removes a small part of that sugar, the acetyl group. Think of it as loosening the name tag slightly.
Preparing it for removal.
Exactly. Then the second enzyme, the galactosaminidase, comes in and makes the cut. It breaks the chemical bond, holding the main part of the A sugar onto the underlying structure. SNP. And once that N-acetylgalactosamine is gone, what's left exposed on the cell surface is the H-antigen.
Which is the universal one, the O-type base.
Correct. It's the foundation that A and B antigens are built upon. So removing the A just reveals the universal H underneath, like stripping red paint off a car to reveal the neutral primer.
That's a great analogy. What made these particular enzymes so much better than previous attempts?
Their efficiency and specificity. They work really well together, very fast. And they are highly specific just for that type A sugar structure.
Yeah.
They don't seem to damage other important molecules on the organ surface.
And they work at low concentrations.
Remarkably low, yes. Just micrograms per milliliter needed, which is key for practical application.
Okay, so they work well in a test tube, but translating that to a whole organ, a kidney that needs to be kept cold, that sounds like a big jump.
It was the next major hurdle. Organ preservation is critical. When an organ is retrieved, it's usually put on what's called hypothermic machine perfusion, or HMP.
Cold storage, basically.
Yes, typically around 4 degrees Celsius. A special cold solution is pumped gently through the organ's blood vessels to keep the cells alive, but quiet, slowing down metabolism.
But enzymes usually like body temperature, right? Around 37 Celsius. How do you get these molecular scissors to work effectively in near freezing conditions?
That required a lot of optimization. The team tested the enzymes in standard cold preservation fluids, like the common University of Wisconsin solution. They found the enzymes worked best in a specific kidney perfusion solution called KPS1, but they needed to enhance the activity further.
How did they boost it?
They modified the KPS1 solution by adding something called dextran 40. This led to their optimized buffer, which they called KD40.
Dextran 40. The paper called it a molecular crowder. What does that mean? How does it help?
It's a fascinating concept. Dextran 40 is a large sugar polymer. When you add it to the solution, it essentially takes up space, physically crowding the other molecules, the enzymes and the antigens on the vessel walls closer together.
So it increases the chances of them bumping into each other.
Exactly. It increases the effective concentration in the microenvironment around the vessel surface, making the enzyme-antigen interactions happen more frequently and efficiently, even at that low 4-degree temperature.
That's clever. So it's like forcing them together in a crowded room.
That's a good way to think about it. And it worked. Using this KD40 solution with the enzymes, they could achieve over 99% removal of A-antigens from red blood cells very quickly.
And on the actual target, the whole kidneys.
When they perfused whole human type A1 kidneys with the enzyme cocktail in the KD40 solution using H&P, they achieved about 92.8% removal of the A-antigen across the organ within just 2 hours.
2 hours. That's fast. And 92.8% removal. Is that considered enough?
It appears to be enough to prevent that immediate catastrophic hyperacute rejection. Getting rid of over 90% of the name tags seems to provide that initial protection.
And you mentioned type A1 kidneys specifically. Why is that significant?
There are subtypes of type A. A1 is the most common, and it has a higher density of A antigens on the cell surfaces compared to the rarer A2 subtype.
So A1 is immunologically louder, more likely to cause rejection.
Precisely. Some older ABO techniques were often limited to using the less immunogenic A2 kidneys. The fact that this enzyme approach worked well on A1 kidneys suggests it could be applied to the vast majority of type A donors.
Opening up a much larger potential pool of organs. All right, section 3. This is where it gets really critical. We have this enzyme-converted organ, an EKO kidney. It looks good on paper. The antigens are mostly gone. But the huge question is, how does it fare inside a living, breathing well, almost living human immune system?
Exactly. Lab tests can only tell you so much. You need to see how it interacts with the full complexity of human immunity, the antibodies, the complement system, the inflammatory cells. That's why they used a human decedent model.
Explain that model. What was the setup for this first-in-human test?
Okay, so the organ was a type A1 kidney. It came from a donor, but unfortunately couldn't be used for a clinical transplant for other reasons. So it became available for this research. They treated it with the 2-hour enzyme protocol using that optimized KD40 solution on the HMP machine.
So it became an EKO kidney. And the recipient?
The recipient was a brain-dead male patient who was type O. Crucially, he was chosen because he had naturally high levels, a high titer of those anti-A antibodies already circulating in his blood. The measurement was 1.256, which is considered quite high.
So they deliberately chose a challenging scenario, a high-antigen kidney going into a recipient with lots of pre-existing antibodies against it.
Yes. They wanted to really test the limits of the enzyme protection. And importantly, this recipient received absolutely no prior desensitization treatment. No plasmapheresis, no heavy immunosuppression beforehand.
Wow. So it was a direct test. Could the enzyme treatment alone prevent immediate rejection in a high-risk mismatch?
Precisely. Using a decedent model like this provides invaluable data on the real biological response without risking the life of a living patient. They could monitor things incredibly closely.
So the moment of truth, they transplant the EKO kidney. What happened immediately? Did they see that dreaded hyperacute rejection?
No, they did not. And that was the first major success. The kidney immediately pinked up. Once blood flow was restored, it felt normal, had good pulses, all visual signs that the blood vessels weren't being instantly destroyed.
And did it function?
Yes. It started producing urine quite well, about 1,300 milliliters in the first 24 hours. So the initial catastrophic event was completely avoided. The enzyme shield held.
Okay, that's huge. It proves the concept works initially. But the real treasure trove of data from this study came from what happened next, right? Tracking how long that shield lasted.
This is the absolute key finding for moving forward. The researchers meticulously tracked the reappearance, the regeneration of the A-antigen on the kidney's blood vessel cells over the next 7 days. They used frequent biopsies and special staining techniques.
When did the A name tags start coming back? What was the timeline?
The regrowth became clearly detectable around day 2 post-transplant. At the 48-hour mark, their analysis showed that roughly 47.5% of the A-antigen had re-expressed on the endothelial cells.
Almost half the name tags were back after just 2 days.
Yes. The cells were starting to rebuild what the enzymes had removed.
And how did the recipient's immune system react once those antigens started reappearing?
It started to notice. By day 3, they detected the deposition of antibodies onto the kidney vessels. And crucially, they saw C4D deposition.
C4D, that's a marker of the complement system being activated, right? The aggressive part of the immune response.
Exactly. Seeing C4D means the immune system isn't just binding antibodies, it's actively initiating the attack cascade on the graft. It's the early warning sign of trouble.
So day 3, the alarm bells are ringing. What happened by day 4?
By day 4, based on the biopsy findings, the histology, they formally diagnosed active antibody-mediated rejection, or AMR. The timing lined up perfectly with that robust re-expression of the A-antigen. The immune system was now fully engaged in attacking the regenerated name tags.
And this attack correlated with the antibody levels in the recipient's blood.
Very closely. They tracked the antibody titer. Remember, it started at 1.256. By day 6, it had shot up to 1.1024.
A 4-fold increase.
Yes. That surge in specific antibodies led to worsening inflammation in the kidney's small blood vessels and increasing tissue damage.
Okay, so rejection did eventually occur as the antigens returned. But how did this compare to what normally happens in an untreated mismatch, that immediate hyperacute failure?
That's a critical comparison. The researchers specifically compared the pathology scores from the biopsies of the ECO kidney with historical data from 2 cases of immediate catastrophic hyperacute rejection.
And
while the ECO kidney definitely showed signs of rejection linked to the antigen regeneration, the severity scores for damage were significantly lower than those seen in the immediate hyperacute cases.
so the enzyme treatment didn't prevent rejection indefinitely, but it absolutely prevented the immediate disaster and lessened the severity, buying significant time.
Exactly. It proved the initial protection was real and effective, pushing the problem from minutes to days.
Now, there's a really important detail about how they got this data. You mentioned frequent biopsies. How frequent?
This is key context. They performed 40 biopsies on that single kidney over the 7-day study period.
40? That's a lot.
It's an extraordinary number.
Yeah.
You would never, ever do that in a standard clinical transplant. Each biopsy causes some physical trauma to the organ.
So the process of collecting the data itself likely contributed to the kidney deteriorating over the week.
It almost certainly did. The primary goal here wasn't long-term graft survival in this specific model. It was to get unprecedented, detailed data on the kinetics, the timing of antigen regeneration, and the resulting immune response. And they got it.
Okay, so despite the eventual rejection in this specific intensely studied model, the implications seem really positive. The biggest one being access to more organs.
Without a doubt. This donor-centric approach, by successfully navigating that initial hyperacute rejection phase using organs like type A1 kidneys from deceased donors, could dramatically increase the number of kidneys available.
Especially for type O patients.
Especially for type O patients. It directly addresses what the paper calls the fairness of and access to organ allocation. More potential donors means shorter waiting times.
And using type A1, the high-density antigen type, is a big deal too. It suggests the method is robust.
Yes, it implies it could work for the majority of type A donors, not just a select few, maximizing the impact on the donor pool.
Now, we have to be fair about the limitations. As you said, this was just one kidney, one recipient model, and the recipient was in a complex medical state.
Absolutely. More research and trials are needed. But the fact that rejection occurred after antigen regeneration actually revealed the path forward.
It defined the next problem to solve. We know the enzymes work initially. The challenge shifted.
It shifted from, can we remove the antigens?
Yeah.
To, how do we keep the antigens gone long enough for the recipient's body to adapt?
Which brings in this concept of accommodation. What exactly is that, and why is it the long-term goal?
Accommodation is a fascinating state in transplantation. It's when the transplanted organ, the allograft, somehow learns to tolerate the recipient's immune environment. It develops resistance to antibody-mediated injury, even if some of those anti-graft antibodies are still floating around.
So the organ isn't just passively surviving because of immunosuppression drugs, it's actively protecting itself.
In a way, yes. It's a dynamic process where the organ adjusts. This usually takes some time to develop, typically maybe 2 to 3 weeks post-transplant.
Okay, so the goal is to keep the antigens low for those first few weeks until accommodation kicks in. Did the ECO kidney in the study show any hints that it was trying to accommodate, even as the rejection was starting?
Remarkably, yes. The researchers did single-cell sequencing analysis on the kidney tissue, specifically looking at the endothelial cells lining the blood vessels on day 7. They were looking for changes in gene activity.
What did they find? Were the cells trying to defend themselves?
They found upregulation increased activity of several genes known to be protective, For instance, genes that inhibit that complement system we talked about,
Yeah.
like CD55 and cholesterol.
The C-aportium marker showed complement was attacking, so the cells were trying to produce their own brakes for that system.
That's the interpretation, yes. They were trying to dampen down that inflammatory cascade. They also saw increased expression of anti-apoptosis genes like HMOX1.
Apoptosis is programmed cell death.
Right. When cells get stressed or attacked, they can trigger self-destruction. Upregulating anti-apoptosis genes suggests the cells were trying to resist dying, trying to enhance their own survival despite the immune assault.
Wow. So even as the antigens were coming back and triggering rejection, the organ itself was showing early molecular signs of trying to adapt and protect itself.
It suggests that the initial enzyme treatment bought enough time for these intrinsic protective mechanisms within the organ to start activating. The chemical engineering provided a window for the biology to begin responding.
And knowing that the critical window is defined by that 48-hour regeneration time gives a clear target for future strategies.
Absolutely. That kinetic data is the roadmap. It tells clinicians exactly when the protection for the initial enzyme treatment starts to fade and when intervention might be needed.
So what's the plan for future clinical trials? How will they use this 48-hour knowledge?
The thinking is a multi-pronged approach. Optimized immunosuppression will still be crucial, likely started right at transplant. But the key new element will probably involve extending the enzymatic effect inside the patient.
You mean giving the enzymes again after the transplant?
Potentially, yes.
Yeah.
The sources suggest the researchers, likely through the UBC spin-off company Avivo Biomedical, are exploring strategies to re-administer the enzymes, perhaps starting around day 2, just as regeneration begins.
And continue dosing for how long?
Maybe for about 2 weeks or so. The idea would be to continuously mow down the regenerating antigens, keeping their levels very low during that critical period while the organ establishes accommodation.
So you use the enzymes not just for the initial cleanup, but as a temporary targeted therapy post-transplant to bridge the gap until the organ can handle things itself.
That seems to be the strategy. It's a much more targeted approach than just globally suppressing the entire immune system long term. It uses the precise timing learned from this decedent study.
It turns the detailed data from those 40 biopsies into a practical clinical plan. That data justifies moving towards formal clinical trials in living patients. Okay, let's wrap this up. What's the big takeaway from this deep dive?
I think the main point is that this enzyme conversion technology demonstrably works for its initial purpose. It successfully prevents that immediate, catastrophic, hyperacute rejection. It buys crucial time, even in a very high-risk immunological scenario.
It shifts the problem. It's no longer can we get past the first few minutes, but how do we manage the first few weeks?
Precisely. The challenge transforms from an immediate chemical one to a slightly longer-term biological one focused on preventing antigen regeneration until the body's own adaptation accommodation takes over.
And we now have that critical 48-hour timeline thanks to this research.
That's the blueprint. It shows how chemical engineering can create this vital window of opportunity, allowing the organ's own biology, supported by targeted therapy, to establish long-term survival.
So for you listening, the takeaway is this precise timeline that future transplant teams will be working with. This isn't just abstract science, it's a potential revolution in fairness and access.
Think about those thousands of type O patients. This technology offers real hope of shortening those agonizing waits, of making transplantation possible where before it was blocked by blood type.
It truly brings us closer to a future where your blood type might not dictate your chances of receiving a life-saving organ. A future where that biological barrier is overcome.
Thanks for tuning in to the Health Headliner podcast by To-Do Digital. Like and subscribe for more health news and breakthroughs. Stay healthy and informed. See you next time.